So we are very happy to have invited Vicky Chu. She was the project manager of the Cosmic 2 project. Now she has been promoted to be the Deputy Director General of NSPO. But so, even though she's very busy, but she's still able to give us this presentation on Cosmic 2 and Formosa 7. And after her talk, there will be 2 other talks on the scientific results of the Formosa 7 missions. So, Vicky, please go ahead.
Good afternoon. First of all, I would like to thank TSU for inviting me to give this presentation. Radio occultation. Radio occultation can deliver message from a signal path. This technique is applied to NSPO's Formosa 3 and the Formosa 7 program. And secondly, I would like to apologize that I cannot join this webinar online, but I will join the Google Meeting Q&A section afterwards. My name is Vicky Chu. I work for Formosa 7 program and Formosa 7 program at NSPO. And first of all, I would like to clarify the concept of radio occultation. I need to switch to Mandarin channel for a while to explain the radio occultation. 衍星呢，是一个天文现象，是指一个天体呢，在另一个天体与观测者之间通过而产生的遮蔽的现象。也就是说，你可以想象，看到这个左下角这个画面，你可以想象你在看这个图，所以你是一个观测者。那么当你在看这个带有绿点的这个星体呢，它是被这个带有红点这个星体所遮蔽的。所以呢，衍星翻成中文呢叫做衍星，所以很容易让人家联想到它是一个在视觉上是有一个挡道的一个现象。那么我为什么特别要用中文解释呢？因为当我们翻译成无线电衍星的时候，那么英文叫做 radio occultation。那么这时候呢，人们可能误会到说，的确是有一个东西呢挡在这个讯号源跟接收机之间。那其实不是这样子的，它并不是有一个固体的物质挡住了这个讯号源和接收机。那你看右下角这个图啊，那讯号源如果没有经过大气层的话，它是直直的到接收机1这里来。但是讯号源和接收机2之间呢，你看到它是有一个大气层。那个大气层呢，就遮在这个讯号源跟接收机之间呢，那它的路径呢产生了一个弯曲的现象。那这个弯曲的现象呢，就叫做无线电衍星。那这个是从英文翻译过来的 radio occultation。但是呢，在这里它并不是说有一个固体的物质呢，它就是一个solid 的一个东西呢，它挡住了这个讯号源跟接收机，而是在中间呢，它是一个介质，它可以是大气层，也可以是电离层。Since afterwards we will have more explanation on radio occultation and occultation in English, so I won't repeat what I have said in Mandarin. Okay. This is the first time people apply radio occultation technique. That's on Marina 4. Marina 4 was launched in 1964, and when it was launched, people haven't thought about people can apply the radio occultation technique on that, because mainly the mission is to take a photo of Mars. But when it has been launched and haven't reached the Mars, there are smart scientists from JPL think we can use the radio occultation technique to measure the atmosphere of Mars. So from this slide, the Earth is on our left-hand side, and the globe here is Mars. So when Mariner to the back of Mars in terms of the view of the Earth, people can measure the occultation by transmitting the signal from Mariner 4 and received by the ground station on the Earth. This was a quite successful experiment. So afterwards, people measured the atmosphere of the other planet for outer space mission. Therefore, people may ask why we apply this technique on the Earth. Yes, people did. Remember that if we want to apply the radio occultation technique, we need two satellites. One satellite to transmit the signal, the other satellite receive the signal. So people did some experiment by two satellites, but the price is too expensive. Until 1994, when U.S. deployed the GPS Constellation in the space of the Earth, of course. So people can begin to think about to use the GPS signal to employ the radio occultation technique to measure the parameters of atmospheric and ionosphere. In 1995, there's a payload called GPS MET on board NARLabs satellite. It did a measurement of GPS radio occultation, and you can see the plot on the right hand side. The measurement is quite consistent with the measurement of radio sound. So this is quite encouragement. Therefore, UCAT sought the cooperation with NSPO for Formoset 3, and in the United States it's called Cosmic. So from this slide, you can easily understand the methodology. When satellite GPS transmits signal, and it goes through the atmosphere and the ionosphere, and the bending angle, people can retrieve the message from the bending angle. And after Formoset 3 is launched to space, it is called the most accurate thermometer in the space. So when there is occultation, we can collect a profile. Although in the beginning it's a kind of bending angle, but through process is a profile of the temperature and the moisture, you can see from the right hand side. And of course, when people compare the retrieve message, a retrieve profile with the sounding blue measurement, they found it is quite consistent. So that's why it's called the most accurate thermometer in the space. From the right hand side, lower panel, you can see there are 6 cell lines for Formoset 3 and with high inclination angle. So that the data distribution is something like this. You can see the green dot. That's the hour measurement. Before we checking the green dot, I would like to explain the red dot more. The red dot is the place sending the sounding bloom, so that people can measure the atmospheric parameters there. However, the red dot is very concentrated on the land mass and even in the place with a high population. So that's why we need the green dot. That's the measurement from Formoset 3. It can cover the measurement from the sea, from Antarctic and the Arctic. That would be very helpful for the weather forecast. This is the comparison between Formoset 3 and the Formoset 7 constellation. For Formoset 3, we have 6 microsatellites, and the payload instrument is capable of measure GPS, radio occultation signal. The orbital inclination is 72 degrees, so that it can collect the data over the globe. Formoset 7 is bigger than Formoset 3. It's a small satellite. We had 6 of them too. Formoset 7 is capable of measuring GPS and the GLONASS signal. The orbital inclination is 24 degrees, so that it can collect the data from middle and low latitude. This is a real data distribution from Formoset 7. You can see it's in the band of north-south 50-degree latitude. This slide shows you the mission architecture of Formoset 7. The joint team used a launch vehicle to send the all 6 satellites to an injection orbit. And the payload on board Formoset 7 satellite, it can collect the data, the radio occultation signal from GPS and the GLONASS FDMA. And once the satellite has collected the data, it's sent to the TTNC station on the ground. And I will show you how many ground stations we have afterwards. Between those ground stations, there are 2 ground stations can send in command, which include Taiwan station and Darwin station. We can send command to configure the satellite and control the satellite. And when those ground stations collect the data or receive the data from the satellite, the data will be transmitted to U.S. Data Processing Center and the Taiwan Data Processing Center. And the data, after the data has been processed, it will be distributed to users and the researchers. Similar to Formoset 3 program, Formoset 7 in the US is called Cosmic 2 program, is a Taiwan-US cooperation program. The basis is an AIT Tegro agreement. And the representative of Taiwan is NSPO, and the representative of US is NOAA. And NOAA, NSPO will report to NARLabs and most and NOAA will report to DOC. Between NSPO and NOAA, we have a Joint Program Management Office, which is virtual. We have a lot of telecom. Sometimes we have 3 telecom per week to communicate the program management and interface issue and integration, how we integrate together. The data product from neutral ionosphere include bending angle profile, reflectivity profile, temperature profile, a geopotential height profile. And the data product from the ionosphere and the space weather includes total electron contents, electron density profile, scintillation amplitude index, and the scintillation phase index. The data requirement for this profile is we need to collect the more than 4,000 profile per day, which you can see from the previous slide that we can achieve that, no problem. The requirement for data latency is 45 minutes for atmosphere. Let me take time to explain what is data latency, because if we want to make the weather prediction, the weather center need the data very quickly. The data latency is from the point the measurement is collect to the point data has been processed, could be assimilated into the NWP, numerical weather prediction model. That's what we call data latency. And the 45 minutes here is a median number, which means 50% of data is within 45 minutes. For space weather, the requirement is more tough. The data latency requirement is 30 minutes. So people may feel curious how we achieve the data latency like that, 45 minutes and 30 minutes. In this joint program, we have a lot of ground stations that include the USA, Tahiti, Honduras, Brazil, Ghana, Kuwait, Mauritius, Taiwan, Guam, and Australia. And based upon the current analysis, we can achieve at least 45 minutes data latency for atmosphere with the 9 ground stations. Please note that the French, the Tahiti ground station haven't been ready yet. It will join the program later on. This slide gives you some idea of our mission payload and science payload. The mission payload of Formosa 7 we call TGIS. It can measure the amplitude and the phase group delay of GNSS signal. And you can see from the left-hand side, the picture, there are RO antenna, which can measure the radio occultation from troposphere. And there are POD antenna. It can measure the radio occultation from ionosphere. And in the middle, there's a receiver which is put inside the spacecraft body. That's TGIS. And we have 2 science payload. One is called IBM. IBM can measure the in situ density, ion density, drifts, temperature, and the composition. So you can see from in the middle of this slide. The upper one is the sensor plate. The lower one is the electronic unit, which is inside the spacecraft. And there is another science payload called R beacon. It is to measure the electron contents and atmospheric scintillation. On the right hand side, you can see the upper one is the antenna, the lower one is the electronics. Again, for all 6 satellites, we have identical mission payload and science payload. This slide gives you some idea about the Formosa 7 satellite. The shape is cuboid unilateral low solar array. The size is about 125 centimeter. The mass is about 300 kilogram weight. The communication capability is we are using S-band. The uplink is 32 kilobit per second. The downlink is 2 megabit per second. And this satellite can support to store 2 gigabit of data from payload instrument, and 3 payload. The weight of 3 payload is 39.4, and three of them need the power of 95 watts in total. And you can see from the this slide, you can see the RO antenna, POD antenna, and in the direction of flight, you can see the IVN, the sensor plate. You also can see the separation system, and this is the ring will connect to the launch vehicle adapter, and you will see that later on. And you can see the structure in this slide. You can see some sensor. You can see deployed solar array. And in this slide, you can see the panel we call NARLabs direction, which is point to the Earth. So that's the bottom panel of the satellite. And you can see the R beacon antenna, and you can see the transmitter antenna. You can see the star camera and the talk rod from this slide. Remembering I ever mentioned about the separation ring. The separation ring is the panel is the one you see here to connect to the launch vehicle adapter. Formosa 7 is take the ride of a Vulcan Heavy, and the mission is called STP-2. STP-2 carried 24 satellites into this space, and Formosa 7 satellites are 6 of them. The interface we call as the S-bar grounded ring. Formosa 7 used 2 rings. You can see 2 of them is attached to the upper ring, and 4 of them are attached to the lower ring. All 6 satellites was injected to an injection altitude of 720 kilometers. And you can imagine that when they separate from the launch vehicle, all 6 satellites are very close each other. So, as I mentioned before, if you remember, for Formosa 3 and Formosa 7, we need the constellation in different orbital plane. How we achieve that? Please remember that the Earth itself is not a perfect sphere. it's a little bit fatter in the at the direction of equator, and it's a little thinner in polar direction. So I put the equation over there. So if we put the satellite in different altitude, that's the A I show in the equation, which is the semi-major axis. Through time, the orbital plane will become different. So therefore, we need to maneuver all 6 satellites one by one every 108 days. So we adjust the FS701 from 720 to 550 about 1 month after it has been launched. Then after that, we adjust their altitude one by one. From the middle of this slide, you can see the constellation is a real constellation in November of 2019. You can see only one orbital plane has been separate from the others, which you can see is FS701. And on the right hand side, you can see the constellation for real on 23rd of February, which is after we complete all the maneuvers. You can see all 6 satellites has been deployed in 6 different orbital planes. When the engineering team doing the orbital adjustment and the orbital maneuver, the science team is busy in to evaluate the Formosa 7 data, and this slide is made by Central Weather Bureau. What they told us is if they put the Formosa 7 data into the forecast, the typhoon track prediction error can be improved by 7% in terms of 120-hour prediction. And the Formosa 7 data has been included in Central Weather Bureau's NWP system. This slide is made by National Cheng Kung University. Perhaps Dr. Charles Lin can provide more insight on this slide. What I want to say here is the observation of ionosphere can provide the researcher and the university more data to understand what happened in the ionosphere. The data through collaboration and validation has been put in the website already. You can get the radio occultation data for ionosphere in the first website, and you can get the ionosphere data from the second website, and you can take a look of the space weather monitoring and the prediction information from the third website. Before I conclude this presentation, I would like to play a video made by UCAR to give another review for Formosa 7 and the Formosa 3. Thank you.
COSMIC is a constellation of satellites that orbit the Earth and provide measurements of temperature, pressure, and moisture in the atmosphere. These measurements are important, and it helps weather forecasting because it gives us an understanding of what the atmosphere is doing at different levels in the atmosphere.
The Cosmic 1 program, which was 6 satellites launched in 2006, was sponsored by a number of agencies. The National Science Foundation, NOAA, and UCAR actually carried out the program with the sponsorship of these agencies and with the cooperation of the National Space Program Office in Taiwan.
3, 2, 1, and 0, and liftoff.
With the advent of new space technology and the ability to launch larger amounts of mass into orbit, we're able to put multiple satellites into separate orbits, and this is very beneficial for the Cosmic 2 program.
With the Cosmic 2 Formosat 7 mission, NOAA is leveraging the large, significant investment that the National Space Organization in Taiwan has made to procure the spacecraft, as well as operate the command and control facilities.
The implementation of Formosat 7 has promoted substantial scientific and technological cooperation and diplomacy between Taiwan and the United States. Taiwan team is responsible for joint program management, mission system, design of spacecraft bus, satellite integration, mission operations, satellite operation, and the control centers.
Cosmic 2 is very exciting because now we're going to have measurements around the equator, especially in areas where there is a lot of hurricanes.
To forecast our weather 3 days or 5 days or 7 days out, we need to know about the weather that's forming upstream from us. That might be as far away as Africa to the east, where the tropical depressions that grow into hurricanes form.
For hurricane prediction, the most important element is the moisture and its variation. 90% of weather is associated with the moisture in the air. Rainfall, clouds, hail, snow, they all are related to the change of the moisture.
The Air Force partnered with NOAA to provide the sensory suite for Cosmic 2. That includes all the sensors, so we have 3 sensors on each spacecraft.
The signals from navigation satellites can actually be used to take measurements of the state of the atmosphere.
The primary payload and the primary sensor is TGRS, which is Tri-Global Navigation Receiver System, essentially. And what TGRS does is it basically measures the changes in radio signals, GPS signals, as they propagate through the Earth's atmosphere. GNSS is the term used for all global navigation satellite systems. So essentially, US GPS is an example of that.
The signals from these satellites pass through the atmosphere, and when they do that, they bend and slow down just a little bit.
So the bending of the radio waves follows the same principle as the bending of a laser beam that passes from the air into a glass of water.
So at the moment when it bends through the atmosphere, the science can retrieve very important measurements for weather. So therefore it gives a very nice uniform measurement of the whole globe.
It's going to provide a wealth of measurements that we can use for our numerical weather prediction models. It'll provide more than 6,000 measurements with higher accuracy than any other method that we have.
Numerical weather prediction is a system we use to forecast the weather. And this system includes instruments that measure the weather and the temperature. It includes a numerical weather model, and it includes very big computers to process all of these data and produce forecasts. The more accurate data you have going into your system, the more accurate your forecast will be coming out.
Radio occultation data are important for climate studies because we now have a record that spans more than 20 years from COSMIC, and having this accurate data set helps us study the changing climate of the Earth.
Space weather impacts systems that we use on the Earth, like our cellular communication systems, our navigation systems, and even our aircraft.
The IVM and RFB are both secondary sensors. What they do is they provide measurements for electric field and electronic content in the ionosphere.
Space weather happens above the clouds, and instead of clouds that we can see, we have areas of charged particles in the ionosphere. And knowing the geographic regions where the ionosphere is active helps us understand how it's going to affect communication systems that we use here on Earth.
I'm excited about the new capabilities that the sensor suite will provide in terms of space weather. This is cutting-edge data that will be flowing into our military data centers as well as NOAA's Space Weather Prediction Center.
We're excited for COSMIC 2 because it can help us to better anticipate and forecast ionospheric effects and their impact on communications and GPS signals.
Radio occultations have been shown to be of the top 5 most impactful types of inputs that you can put in numerical prediction models to reduce the forecast error.
The sensor suite is fulfilling a gap and providing a capability that we do not currently have in space weather and terrestrial weather.
COSMIC 2 will provide 10 times the number of measurements that previous systems provided. And these measurements will help us improve our weather forecasting in the future.
Anyone of you have questions, please either raise your hand or unmute yourself. Okay, while waiting for people to think about questions, I have 1 or 2 questions to ask you, because in the presentation in your talk, you talk about the 7% improvement in the calculation or prediction of the typhoon tracks. How do you calculate it? I mean, the 7% is a compared with Formosa. I mean, the COSMIC 1, or I mean, what is the reference point?
Okay, the 7% is compared to with Formosa 7 assimilate into the NWP, and without Formosa 7 data assimilate into NWP. So by this way, we can demonstrate the impact of Formosa 7 data.
But what do you mean by 7%? 7% in what sense? I mean, because it's closer to the actual track, or what?
It's that yes, it's closer to the actual track, and that's better.
So it's not easy to understand the quantitatively. What does it mean by 7% in the improvement? Of course, we believe that it's a very important improvement. The second question I have is that originally you had I think 12 CubeSat, right? 12 satellites. I mean that another half dozen are going into the near high altitude or high latitude orbits, and they are not there. And are they important? Are they? Is it necessary to how to say to add them back to the mission?
The reason that we don't have the second 6 satellite because the commercial company in the United States convinced their senator that those data are very valuable, so that the commercial or private sector want to launch their own satellite to sell the weather data to somebody like government. And President Trump passed the bill of like to encourage the private sector to join, or they can provide the data to NOAA for evaluation. If the data is good, NOAA will try to procure the data from private sector. So that's why we don't have the second set of the 6 satellites. And as for the second set of satellites are important to the weather forecast. As you know, if we calculate something, we need to have a boundary condition. So if we only have the data from the mid and low latitude, the boundary condition is some kind of not so clear or so good or so certain until we have the global data. So
Yes.
that's my response.
Yes, I understand that. But are the second satellites now in place now, or what? Are they making money?
From government or federal, I don't think we will go back to from government's funding to have the second set of satellite. However, some private sector like SPIRE or the other private company, they already have some data for and have those data to be evaluated by some researchers. I don't know how good they are.
So it will be interesting anyway. I mean, if they are useful, it will be interesting to combine them with your with the Formosa 7 measurements to to make the prediction even better.
I don't currently I don't have the data available around me, but I do remember they try to invite some of us to evaluate if the SPIRE data is good or not. So I can try to dig out the email to find out the link, so people can get into the site to do the evaluation.
Very good, because the next two talks will be given by the researchers who are using the data. Maybe we could ask them that question also.
Okay.
Yeah. The other thing is this: that we saw that at the end you saw this video, very nice, made by the Americans.
Right.
Can NSPO produce your own version? I mean, by inviting the scientists and the engineers and the users to to more or less to advertise how important this issue is. You have the money, right?
No, I need to check with our promotion division to see if we want to do that or not, because NSPO have different kind of video to record from INT and the early operation phases. But as you say, we don't have a video to do the science part, to have a public education.
Right. This is very important.
Yeah, I know what you mean. I need to check with Mei-Ling Chen, our promotion division head, to see if we can do that or not.
Yeah, please do. Any other questions from the audience? I mean, nowadays it's very lucky that we have Vicky here talking to us in person in real life. If you could sit down and wait for the next talk and so on, maybe you could ask them questions, too, right?
So I wonder, when you do these measurements with radio occultation, I wonder, essentially, when you have two satellites in orbit and you get your smearing effect due to the atmosphere, and you essentially get a measurement for this entire segment of the atmosphere that your signals pass through. How do you then get fine-grained measurements? Because what you would essentially get is like an arc segment of, I don't know, maybe 20, 30 degrees or something of the atmosphere, or depending on what elevation you have with your satellites. Do you then get a much finer measurements by combining the data from multiple satellites, or how does that work?
Okay. What you say is not what we do, but I think UCAR an organization in the United States, they do combine different kind of radio occultation satellite and put them together so that people can use can use the radio occultation data from different program. However, in Taiwan, the website I introduced to you guys only contain the radio occultation data from Formoset 7 and Formoset 3 program.
Ah, okay. All right, so you combine multiple. Okay, thank you very much.
Thank you.
Thank you.
Vicky, thank you so much.